So I agree that there are open questions that even string theory, as it's currently formulated, doesn't doesn't address.
Famous physicist Sir Roger Penrose just announced that string theory has lied to us for 30 years.
Well, I think the trouble with string theory is that there isn't any connection with observations. As far as I'm probably taking too strong a view here, but the mathematics, I mean, it's largely driven by the mathematics as far as I know, which is in itself is not an objection as far as I'm concerned. A lot of what I do is driven by the mathematics. But the trouble with string theory is it's supposed to be a theory of the way the world operates. And if the number of dimensions of space is just wrong, I can't take it seriously.
String theory is a concept in physics that states that the universe is constructed by tiny vibrating strings, smaller than the smallest subatomic particles. As these fundamental strings twist, fold, and vibrate, they create matter, energy, and all sorts of phenomena that make up our entire universe. This theory has been promoted as a revolutionary concept that will change the world, but it has not delivered on its promises and remains untestable.
If you could have a theory which had predictions, and these predictions could be seen to be right or wrong, that's what I understand about physics. But string theory seems to me driven largely by certain ideas which have importance in mathematics, but sort of irrelevant to the physics, really. As far as I know, there's places where string theory has had an impact on mathematics. Sure, it has, but it's not physics, as far as I can see. So the main trouble I have with string theory is I don't think it's physics.
String theorists are seen as liars, with the public feeling deceived after waiting for the next big thing in physics for 30 years. The public feels angry and lied to by string theorists who claim that the future of physics is string theory, when in reality, it was never the case.
I would take a somewhat different perspective than Rogers. Quantum mechanics is an established part of the way the world works. General relativity is an established part of the way the world works. If they can't play together, if when you combine them, you get nonsensical results, which was the state of play before string theory gave us a potential solution, then your physical description of the world is fundamentally inconsistent. And I don't think the universe is inconsistent, and therefore it is vital that we find a way to put the pillars of our previous understanding into harmony with one another. Eric mentioned perhaps there are other ways of doing it. Fantastic. I'm open to those ideas. But string theory, at least, is one approach that does that. And it's important, it's vital, and string theory not only achieves it, but to the question of beauty, let me just put forward the following. You do quantum mechanics of a string without any knowledge of general relativity. And just through the process of studying that quantum mechanical description of the string, general relativity emerges. It's forced upon you. It comes right out of the mathematics. If Einstein hadn't discovered general relativity, string theorists studying the quantum mechanical motion of a string would have found general relativity within the formulation itself. That's beautiful. That's breathtaking.
Roger Penrose is one of those individuals who believe that string theory is flawed, and we have been lied to for decades. But why does Roger Penrose believe that string theory is a lie?
I mean, the trouble is that they claim it's such a beautiful theory. As far as I can see, it's a great mess. I mean, you've got the wrong number of space dimensions. You've got an argument to try and argue that you don't get enough energy to excite the extra dimensions. I mean, I think that argument is wrong, actually, because the amount of energy is for the entire universe. It's not that you're building an accelerator to get up to a certain energy that's beyond the level of that accelerator. That's not the point. You've got that much energy, and all over the universe, things with a great deal of energy, and there's no reason why these shouldn't excite these extra dimensions. I think there's just a misconception in that. I don't want to go into it further, but it's a bit technical, but I think it's a misconception. And in a certain sense, there are too many theoretical physics communities which have wasted their time on this area rather than doing what I regard as more interesting topics.
In the late 1960s, string theory began to be widely explored, initially under the name of nuclear force. However, it later shifted away from nuclear force and started being applied to various concepts in quantum chromodynamics. This led to the realization that string theory isn't traditionally applied to nuclear physics theories, raising concerns for the quantum theory of gravity. The earliest version of modern string theory was bosonic string theory, which only included and described a class of particles known as bosons. This was followed by superstring theory, which described connections between symmetry and bosons, known as fermions. In the mid-1990s, more than 5 versions of superstring theory emerged, but they fragmented the theory into nearly 11 dimensions, known as M-theory. The link between string theory and quantum field theory was established in the late 1990s, famously known as the ADS-CFT correspondence. The idea of the fifth dimension in gravity theory dates back to 1914, when Gunnar Nordstrom proposed it to describe both electromagnetism and gravity. He attempted to explain electromagnetism with his gravity theory, making the first modification to string theory. Einstein later replaced this with a non-symmetric matrix sensor. And much later, Branes and Dick expanded on this idea by introducing the scalar component of gravity. These outcomes are considered significant advancements in the realm of string theory. The original idea of string theory emerged between 1960 and 1970. During that era, theorists didn't explore string theory extensively, as it couldn't fully address issues related to hadrons, protons, neutrons, and other subatomic particles. Despite these early investigations, the evolution or history of string theory can be divided into 2 phases. The first phase is referred to as the first superstring theory, spanning from 1980 to 1994. At the start of this period, it was found that a neutrino, a chiral fermion, couldn't be explained by any quantum gravity theory. Edward Witten played a key role in this research. Consequently, he collaborated with Luis Alvarez Gaume and delved deeper into the study of conservation laws, a part of anomaly gravity theory. Later, a new anomaly was found that both researchers overlooked. This led to narrowing down the scope of a string theory group, called the gauge group, to SO. Consequently, Witten became convinced that string theory represents a fully comprehensive framework for the theory of quantum gravity. Through his research, he established himself as a prominent advocate. Hundreds of physicists and mathematicians pursued their studies building upon Witten's research. This occurred between 1984 and 1986, known as the first superstring revolution in string theory. In 1995, a new 11-dimensional theory emerged, now known as M-theory. The period during which M-theory was developed is referred to as the second superstring revolution. Nearly all basic interactions, including gravity, are incorporated into string theory. Consequently, most theorists and physicists argue that string theory is a comprehensive theory capable of explaining everything in our universe. Presently, researchers are exploring string theory to address various issues concerning elementary particles with small cosmological constants, such as dark matter and cosmic inflation. Progress has been made toward these objectives. Therefore, it remains uncertain whether string theory truly serves as a universal theory. As mentioned earlier, string theory has yet to provide a complete framework applicable in all situations, which is considered a significant drawback. Currently, string theory relies on a perturbative approach, and a non-perturbative application has not yet been discovered. Understanding the basics of string theory is crucial to grasp these concepts. In quantum field theory, the application of mechanics to physical objects is presented in an expanded manner. In this theory, the concepts are expanded to include space and time. Different physical events are computed in the realm of quantum theory using techniques from perturbation theory. Feynman diagrams are employed in perturbation theory to organize various calculations. These diagrams represent paths of point-like particles and illustrate the interactions among the particles. Bosonic theory is considered the simplest form of string theory. However, it had a limitation as it only accounted for bosons, which are particles responsible for transmitting force between different matter particles. These particles are distinct from fermions. Superstring theory replaces this version by incorporating both bosons and fermions. It introduces the concept of supersymmetry, a mathematical relationship between bosons and fermions found in various physical theories. Besides supersymmetry, there are several other versions of string theory, such as Type 1, Type 2a, and Type 2b, each introducing new concepts and theoretical approaches. For example, Type 1 includes both open and closed strings, while Type 2a and Type 2b describe closed strings exclusively. Typically, we understand space to have three dimensions: height, width, and length. However, Einstein introduced time as another dimension in his general theory of relativity, forming a four-dimensional space-time. In this theory, Einstein didn't treat time and space separately, but merged them. Space-time organizes the universe into a coherent structure. Some physicists explore additional dimensions to advance approaches in this field. In string theory, an extra dimension is added for mathematical consistency, extracted from four-dimensional space-time. In the bosonic version, space-time has 26 dimensions, reduced to 10 in superstring theory. Efforts have been made to reduce the number of extra dimensions. Physicists believe that the observable universe has a four-dimensional structure, despite high-dimensional space, crucial for developing real-time physics using string theory. Most versions of string theory take distinct approaches. This type of connection between different versions of string theory is known as S-duality. According to this concept, particles that strongly interact in one theory may have very weak interaction in a completely different theory. Another connection among various string theories is T-duality, which states that each string theory wraps around an extra dimension. Duality is when two different systems with different physical concepts are shown to be similar in a significant way. It's important to mention that duality applies only to concepts within string theory, as it doesn't offer consistency in other fields. In a duality relationship, if two theories are related, one can be transformed with some adjustments. However, the operations in these theories can't be made identical since they're based on different principles. Duality means that two different theories share the same phenomena but involve different mathematical operations. For instance, S-duality in quantum theories, like Montanan and Olive duality, connects ADS-CFT, bridging quantum theory and string theory. In string theory and related ideas, branes are recognized as physical entities. They're used to extend the dimensionality of a point particle. For example, particles exist in 0 dimensions, while strings exist in 1 dimension. This is just one illustration. Branes can have much higher dimensions as well. They're dynamic objects governed by the principles of quantum mechanics as they move through space-time, and they have properties like charge and mass. Branes are also explored in pure mathematics. In string theory, D-branes are particularly important as they involve open strings in their concepts and serve as a foundation for string theory's exploration of space-time. During the early period of 1995, many theorists proposed that there are 5 variations of this comprehensive theory: Type 1, Type 2A, Type 2B, Heterotic String Theory 1, and Heterotic String Theory 2. This idea was debunked with the introduction of M-theory. In 1995, Edward Witten suggested that the 5 theories mentioned above are just limited versions of the main 11-dimensional M-theory. This revelation had a significant impact on the field of physics. Numerous physicists quickly delved into further research using M-theory as a foundation, leading to multiple studies now recognized as the second superstring revolution. Supergravity theories combine general relativity with supersymmetry. This theory caught the interest of many theorists and physicists in the 1970s. By 1978, it was found that assuming 11 as the maximum number of dimensions allows for consistent supersymmetry formulation. During the same time, it was shown that supergravity cannot accommodate more than 11 dimensions. Thus, 11 is established as the maximum number of dimensions allowed by supergravity. Thanks to these studies, many physicists began considering the possibility of using supergravity with 11 dimensions to create real-time models of the four-dimensional world. They also hoped that these models would help us better understand fundamental aspects of the four-dimensional world, including electromagnetism, strong nuclear forces, weak nuclear forces, gravity, chirality, a phenomenon that presented a challenge in applying the 11-dimensional concept practically. The issue arose because the fundamental laws of physics distinguish between clockwise and anti-clockwise phenomena. It was later recognized that the 11-dimensional concept is not yet fully developed to address or encompass this problem. During the era of the first superstring revolution, many theorists and physicists had embraced string theory as a fusion of particle physics theory and quantum gravity theory. Supergravity theory couldn't resolve the chirality problem. In contrast, string theory not only addressed the chirality issue, but also offered an updated version of gravity theory, incorporating the concept of quantum effects. However, by the late 1990s, many physicists were debating whether there are fewer than 5 supersymmetric versions of this theory. It's established that string theory has fewer than 5 consistent versions. A unified version of these theories hasn't been created yet. As research progressed, physicists began closely examining and studying string theory. They eventually found that these different versions of string theory are interconnected. Some are intricately related, while others are related in non-trivial ways. It was also found that there isn't much distinction between strongly interacting strings and weakly interacting strings, except for the level of interaction. This concept is referred to as S-duality, as explained earlier. Later on, researchers also uncovered the T-duality connection after a couple of years. According to this concept, two equivalent strings can exist in entirely different space-time and geometries. Meanwhile, some physicists were exploring the application of string theory on high-dimensional objects to describe its properties. In early 1987, two-dimensional branes were identified as part of an 11-dimensional space. These objects resembled sheets and were observed propagating through 11-dimensional space-time. Later, a new idea emerged where one dimension was seen as a curled-up circle. In this concept, imagine the branes wrapped around this circular dimension. Now, imagine that the radius of the circle, or dimension, is small enough so that on a 10-dimensional scale, the branes can be seen as a single string. The arrangement of these objects resembled closely to a string seen in the 2A version of superstring theory. Mathematicians define a matrix as an arrangement of numbers or other data types organized in a rectangular form of specific dimensions. However, in physics, the definition of a matrix differs significantly from the mathematical one. In physics, a specific theory that involves the concept of a matrix in its mathematical description is referred to as a matrix. A matrix model describes the interaction between a group of matrices within the framework of quantum mechanics. In 1997, a small team of researchers presented an important example of the matrix model known as the BFSS matrix. This model involved a set of 9 large matrices. They demonstrated that 11-dimensional supergravity governs the low-energy behavior of any matrix model. These findings established that their BFSS model closely resembles M-theory, leading many researchers to use the BFSS matrix model as a prototype for the original M-theory. The model was utilized to pinpoint the precise formulation of M-theory. Numerous physicists also employed this model to extensively elucidate the properties of M-theory. These studies aided in connecting matrix models with M-theory and establishing a relationship between matrix models and geometry with a non-commutative nature. Building on these findings, many physicists uncovered significant connections between non-commutative geometry and various physical theories. In general, an area of spacetime with an extremely strong gravitational field is called a black hole. Their gravity is so intense that nothing, not even particles or radiation, can escape. According to current research and widely accepted models, black holes form when a large or even small star undergoes gravitational collapse. It's believed that supermassive black holes exist at the center of every galaxy in the universe. Black holes are of particular theoretical significance because many theorists use them as a foundation to study the quantum aspects related to gravity. String theory provides a framework for thermodynamics, which is crucial for studying the properties of black holes based solely on their thermodynamics. Statistical mechanics, a well-established field in physics, deals with the behavior of systems with many particles. Entropy, a concept in statistical mechanics, measures the randomness or disorder of a physical system. It was first studied in the late 1870s. And during that time, Australian researcher Ludwig Boltzmann discovered that the collective behavior of gas molecules could help derive thermodynamic properties of gas. He demonstrated that by manipulating the behavior of gas molecules, one could determine the microscopic properties of gas, including temperature, volume, and pressure. Boltzmann's work showed that entropy is a natural tool used to describe different arrangements of molecules, known as microstates. These findings inspired theorists to explore macroscopic properties of various physical objects. By the early 1900s, researchers and physicists began applying the same idea to black holes, using gases and entropy scales. In the 1970s, Jacob Bekenstein demonstrated that entropy is linked to the surface area of a black hole's event horizon. The event horizon marks the boundary where matter, particles, or radiation are lost due to the intense gravitational pull of the black hole. Combining his findings with Stephen Hawking's, Bekenstein formulated a formula to calculate the entropy S, where c equals speed of light, k equals Boltzmann's constant, h equals reduced Planck constant, g Newton's constant, and a the surface area of the event horizon of the black hole. Each black hole possesses relative entropy similar to any other physical object or system. It correlates with various microstates that exhibit the same macroscopic characteristics mentioned earlier. This equation can determine the expected value of any black hole. However, physicists in the 1990s tried to enumerate microstates in quantum gravity theory, lacking a derivation for the formula. Hence, finding such a derivation is crucial for the validity of any quantum theory, particularly for string theory. String theory encompasses various frameworks serving different purposes. Some of its models are utilized in constructing models for real-world physics, combining particle physics and general relativity. Phenomenology, a branch of theoretical physics, focuses on building real-time models from abstract theoretical concepts. Within string theory, this is referred to as string phenomenology, which explores constructing real or semi-real models solely based on string theory. However, there's no empirical evidence to validate these models due to two main reasons. 1. Theoretical and mathematical challenges. And 2. Practical testing requires extremely high energies, which are currently unattainable. Due to this approach has been criticized by many communities or individual experts. Some also doubt the unifications of questions and values derived through this approach. Standard particle physics models are currently the most widely accepted theories. These models contain detailed information about particles and their interactions, including the study of three fundamental forces: strong nuclear forces, weak nuclear forces, and electromagnetism. However, despite providing descriptive information, these models have fallen short in fully describing real-world phenomena. The primary reason for their limitation is the lack of integration of gravitational force. Additionally, there are minor issues such as hierarchy problems. Standard models fail to fully describe the mass structure of fermions and the nature of dark matter. Beyond the limits of standard models, particle physics models can also be developed using concepts from string theory, with compactification serving as the basis for constructing such models. Physicists proposed a shape for the extra dimension by starting with 10/11th dimensional spacetime. By utilizing this shape properly, similar models to the standard model can be constructed, which also incorporate yet-to-be-discovered particles. To derive real-time physics from string theory, one must apply heterotic theory, assuming 10-dimensional spacetime with nearly 6 extra dimensions. This method provides various approaches to derive real-time physics from string theory. A real or semi-real model of a 4-dimensional universe can also be developed using the same technique with minor adjustments, making it applicable in M-theory as well. The Big Bang Theory is considered the earliest cosmological model, explaining a wide range of evolutions. It successfully accounts for galactic red shifts, abundance of hydrogen and helium as light elements, confirmation of cosmic microwave background radiation. However, the Big Bang Theory leaves many questions unanswered, including: why is the universe nearly uniform in all directions? Why does the universe appear flat on very large distance scales? Why haven't magnetic monopoles and other hypothesized particles been observed in practical experiments? An alternative idea to the Big Bang Theory emerged in the 1980s, called cosmic inflation theory. It incorporates all the principles of the Big Bang Theory as valid, but also provides explanations for some unresolved aspects of the universe. According to this theory, cosmic microwave radiation was dispersed approximately 380,000 years after the Big Bang events, filling the sky as proposed by inflation theory. It's crucial to define a specific shape for the extra dimension in spacetime to develop real-time physics models based on string theory. Each unique shape corresponds to a potential universe, with an arrangement of particles and forces differing from one another. String theory suggests there are approximately 10 to the 500 power vacuum states, or potential universes, capable of explaining phenomena observed at different energy levels. Critics raise concerns about the vast number of possible universes in string theory, arguing it makes predictions nearly impossible. They claim that selecting one option would only apply to that specific universe. However, some experts view this large number as advantageous. They argue that it allows for close observation of physical constants and natural phenomena, including the cosmological constant, which is exceptionally small. While many string theorists acknowledge these points, they don't dismiss string theory entirely. Some see the abundance of universes as a strength, while others consider it a flaw. None of them agree with critics who assert that the theory is entirely incorrect. Background independence is a key aspect of Einstein's general theory of relativity. It implies that formulations within a theory with this property cannot depend on a specific space-time geometry. Some critics argue that string theory lacks this independence since it requires a fixed reference to geometry or space-time. All other geometric calculations are then made in relation to this fixed reference. Critics claim that string theory fails to maintain this crucial feature for each term described in the theory. These points were disputed by some string theorists. Polchinski, one of them, highlighted that developing a holographic description for gravity in quantum gravity theory poses a major challenge, which is why it doesn't need a gravitational field to be anti-de Sitter. This, he argues, is precisely why string theory lacks background independence. In response to Polchinski, Smolin argued that the points raised by Polchinski are potential future outcomes rather than established facts. He pointed out that the foundation of general relativity and quantum gravity relies on global symmetries due to the dynamic nature of space-time geometry. Unfortunately, this debate continues, and the ultimate truth is yet to be discovered. Numerous critics are striving to gain a deeper understanding of string theory to identify and explain its flaws, while on the other hand, some theorists are investigating it to address the gaps. String theory has been a valuable tool for high-energy theoretical physics since the first and second superstring revolutions in the 1980s and 1990s. Several string theorists argue that no other theory can address fundamental physics questions as effectively as string theory. However, many critics disagree with these claims from various string theorists. Peter Voigt, for instance, views string theory negatively, considering it detrimental to the future of pure physics. He believes that the financial structure of academia and intense competition for resources are driving factors behind string theory's popularity. Critics often use Voigt's perspective to form their own opinions on string theory. Statements made by Voigt are widely acknowledged. Even some proponents of string theory acknowledge them as a backup plan. A critic, Penrose, argues that many young researchers opt for using existing frameworks rather than developing new ones themselves. He cites this tendency as a reason for the popularity of string theory among physicists and researchers. Lee Smolin argues that the dominance of string theory hinders the advancement of physics, despite being a theory within physics. He favors following loop quantum gravity theory, which, according to him, promotes the foundational aspects of physics and innovative thinking. So far, no critic or string theorist has been able to prove themselves entirely correct. In simple terms, no critic has disproved string theory entirely, and no theorist has proven it completely correct. The debate continues endlessly up till now. However, some experts remain hopeful that someday it will reach a conclusion. Some acknowledge the flaws in the theory, but strongly believe the debate will persist. String theory encompasses almost all fundamental concepts of modern physics. While it has many loopholes, solutions are still being sought. Some string theorists believe that through continuous research, the theory will eventually become complete. Conversely, some have accepted string theory as it stands. The same applies to critics. Some strive to disprove it entirely, while others have accepted it as incomplete, believing that there are no more unknown errors. As a researcher, student, or practitioner, it's important to acknowledge that the theory is incomplete. This approach allows one to engage with string theory effectively. Paying no heed to criticism can aid practitioners in accepting the concepts and facts presented in the theory. Almost every concept in the theory has been critiqued, so it's advisable to embrace the theory as a whole, recognizing its imperfections or exceptions. Roger Penrose holds the view that string theory is flawed and may not accurately describe the universe. One reason for his skepticism lies in the lack of experimental evidence supporting the string theory. Despite decades of research, There hasn't been any direct empirical confirmation of the existence of these tiny strings proposed by the theory. Penrose also questions the testability of string theory. Unlike other scientific theories that make specific predictions, string theory's complex mathematics often lead to multiple possible outcomes, making it difficult to test empirically. This lack of falsifiability goes against the fundamental principles of scientific inquiry, according to Penrose. Moreover, Penrose advocates for alternative approaches to understanding the universe, such as his own theories in quantum gravity and the role of consciousness in physics. He believes that these alternative frameworks may provide more promising avenues for explaining the mysteries of the cosmos. So that seems enough for today's video. What are your thoughts on string theory? Let us know in the comments below, and please stay tuned for more content.